Today we're going to learn about another application of centroids, and the title of the topic is the Theorem of Pappus and Guldinus. We're going to use centroids to find surface areas and volumes of revolution. You did this back in calculus by setting up integrals, usually using either washers or shells, was how my calc teacher taught it to me. But we're going to learn this Theorem of Pappus and Guldinus today that will allow us to use our knowledge of centroids to find this a little bit more easily. So let me draw an x-axis. This is going to be our axis of revolution. And we're going to start with a part that looks like a straight line, and it jumps up and it goes over some more and down and over some more. And we're going to take that line and we're going to revolve that around the x-axis. When we're done, we'll end up with a shape. That's kind of what the shape's going to look like. So a tube with a section in the middle that's a little bit bigger around. And the idea is if I wanted to find the surface area of that shape, I can do it with calculus by taking a little chunk, a little dl along my blue line. Line goes along like this, and I want to take a little section of it, and I want to find out how much surface area does that generate when it's revolved around the x-axis. So in doing that, you create a little strip that's wrapped all the way around the outside edge of the part, and it's the area of that strip that would be the surface area that dl creates when it's revolved around the x-axis. And what's important in figuring out how much that's going to be is the radius. So the radial location of how far out, I draw down here as a radius, do I have to go from the axis of revolution to generate this? So once we do that, we can find the surface area of the strip, that strip of length dl. Well, that's going to be the width of the strip, dl, times the circumference. So remember, the circumference of a circle is 2 pi times the radius, or pi times the diameter, and then the width is dl. So what if I want to find the total surface area? Well, we integrate. We add them up. We integrate 2 pi r dl, and we integrate it over this blue edge. Well, let's simplify this just a little bit. That would be 2 pi times the integral of r dl. And if you go back and look at centroids, specifically for centroids of a line, we spent most of our time in class talking about centroids of area. But the idea is that the integral of r dl is equal to the centroid location r bar times l. So let me write it down here and show you why it is. This is equal to 2 pi r bar times the total length l, where r bar is the centroid location of that blue line measured from the x-axis, and l is the total length. Now, where does that come from? It comes from the fact that if I wanted to find the centroid location of that, call it r bar or y bar if you want, it's straight up, that's equal to the integral of r dl in this case over the total length dl. And then we just bring that, this is our total length l, we bring it to the other side of the equation, and that's how we figure out that the integral of r dl, sitting right here, is just r bar, the centroid location, times the actual length. That's the idea. We can also do volume. The way we do that is very similar. Let me draw another picture for that one. So let's say I had an area that was just a rectangle, and I revolved that around my x-axis. And it was something like that, hollow tube. So here would be my area. Let me shade it in. We have this area A, we're revolving it around the axis, and we want to find the total volume. So if you'll remember from calculus, the way you would have done that is you find a little area here, dA, and it is located a distance r away from the axis. And so when you rotate that little area about the axis, you get a volume. It'll create a little bit of a ring whose volume is the area dA times how far around it travels. If I wanted to find the total volume, it's going to be the integral of 2 pi r. That is the distance that this travels going around the axis times dA. Well, we'll simplify again. That's going to be 2 pi out in front of the integral times r dA integrated over the whole area. And with the same argument as before, if I have an integral of r instead of dl, it'll be dA, and I divide it by the total area, I get r bar, or you can bring the area to the other side. Doing that, we get that the volume is 2 pi times the centroid location, this would be the centroid of the area, times the total area. So this is the centroid of the area measured from that axis of rotation, in this case, the x-axis, and A is the total area of that green rectangle. So this is what's really cool, is if we can find the centroid of an area and the centroid of a line, we can calculate surface area and volume without needing to do integrals, because we basically already did the integral in finding r bar. We use 2 pi here because in both cases we were revolving all the way around the axis. Well, what if the revolution was less? For partial revolutions, surface area is going to be theta times r bar L, and volume is going to be theta times r bar times the area. And theta must be in radians. Let's try an example. I call this kind of the donut example. It's a big ring-shaped thing. It's basically a circle that's been revolved about an axis that's down here below the circle. And you'll get this nice donut ring shape. We're supposed to find the surface area of the ring. We're also going to find the volume of the ring. So our area is this circle right up here. Let's do volume first. I actually think volume is a little bit easier to figure out. Volume is 2 pi r bar times the area, because we're revolving it all the way around the axis. That's why you use 2 pi. Write down the 2 pi. R bar, that's the distance between the centroid of the area, which is right in the middle of the circle, and the axis of rotation. You'll notice that my whole thing is 8 inches high. Here's a 4-inch gap, which means each of my circles is 2 inches tall. So their centroid would be 1 inch away from either the top or the bottom. And so to get from the middle to the centroid is going to be a 3-inch distance. 3 inches is r bar for the circle. Then the area of a circle is pi times the radius squared. Pi times 1 inch, that gets squared. We multiply it all out and we get 59.2 inches cubed. And we found the volume of revolution without integrating, because we knew how to find the area of a circle and we knew how to find the centroid of a circle. Let's do surface area. That's 2 pi r bar times L. So we'll do the 2 pi again because it's a full revolution. What is r bar? Well, now we're looking at the centroid of the circle, not the centroid of the circular area, but the centroid of, you could imagine it like if I had a piece of wire or something that I had wrapped all the way around the outside of this circle. And it also has a centroid. And the centroid would be, because it's completely symmetric, still right in the middle. So the centroid of the red circle is actually the same exact location as the centroid of the purple circular area. They're both right in the middle of the circle. So let's plug in r bar, which will be 3 inches also. And now the length, instead of doing before we did area, which was pi r squared, this time what we want is the length of the line that goes all the way around the edge of the circle. Well, that's the circumference of that circle. Circumference is pi times the diameter. The diameter of the circle is 2 inches. So there's your length. This up here was our area. And we multiply that out and we get 118 square inches. And that is how many square inches are all over the outside surface of this ring. Pretty simple. No integrals required, but we can find volumes and surface areas of revolution. Let's do one more example. This is a hopper that's filled with coal, and we're supposed to find the volume of coal given a certain void volume fraction. So 35% of the volume of the hopper is voids, is airspace. So we'll use that at the end. First, let's just find the volume of the hopper. What I find really useful with this one is a nice 3D picture, but what we really want is a 2-dimensional shape that gets revolved. So if we want to do the 2-dimensional shape, getting revolved about this z-axis, and it looks like what I have first is a rectangle that's 4 meters high, and it looks like it's 1.5 meters wide. And then at the bottom, it goes in at an angle and then straight across. So I'm probably going to break this up into 3 shapes, a rectangle, and a triangle. And let's put a couple more dimensions on here. That looks like 1.2 meters. We're told this radius in here is 0.2 meters. This length right here is 1.5 minus 0.2, 1.3 meters. And let's color code all of these when we're finding the centroids. So there is one of my shape, the triangle blue. I'll make this little rectangle orange. But what I want to find, if I'm looking for the volume, our equation was volume equals 2 pi r bar times A. Well, r bar can be in any direction. We're measuring out and away from the axis of rotation. So let's find r bar. R bar is equal to the summation of the r tildes times the areas over the summation of all of the areas. So starting out with a green rectangle, looks like its centroid is going to be right here. So since the whole width is 1.5, we'll come out 0.75. 0.75, and then the area is 4 times 1.5 meters, and in the bottom of the fraction we just put the 4 meters and the 1.5 meters. Plus, let's do the blue triangle. Its area is 1/2 base times height. Put that on the bottom. 1.2 times 1.3. On the top we'll have 1/2 times 1.2 times 1.3. But I also need to figure out where in the world is its centroid, and it looks like its centroid location, remember how we'd find centroids of triangles? It's 1/3 of the way away from the kind of the right angle corner. So if this is 1.3 wide, its centroid would be 1/3 of that over plus this little distance. So what I need in here is going to come out to be 0.633 because I calculated it already, but where that comes from is 0.2 plus 1/3 of 1.3. It's the distance from the centroid of this triangle all the way back over to the axis of rotation. Finally, orange rectangle. So the centroid location will be half of the way over, so 0.1 meters, and then the rectangle itself is 0.2 times, and it's 1.2 tall. And then in the bottom of the fraction, we have just the area, 0.2 times 1.2. The top of that comes out to be 5.018 meters cubed, and the bottom is 7.02 meters squared, which happens to be 0.715 meters. Now, you might notice there's a bit of a shortcut here. I just divided something by the area, and now I'm going to plug this in up here and multiply by the area again. So that area is actually going to cancel out, but it's okay. I already did the math. Volume is 2 pi r bar times area. 2 pi r bar is 0.715 meters, and the area is 7.02 meters squared. And again, multiplying that out, this is actually equal to that 5.018 meters cubed I already found. Multiply by the 2 pi, and you get the volume of the hopper, 31.5 meters cubed. There's the volume of the hopper. Next, we need to figure out the volume of the coal, because 35% of that volume is airspace. The voids are 35%. So the easy way to do this is if voids are 35%, then the actual coal is 100 minus, which is 65%. So that's the volume of the hopper. So the volume of the coal is 0.65 times 31.5 meters cubed, which is 20.5 meters cubed. We solved the problem. I want to do one more thing before we're done though. Let's find the outside surface area of this. And get the outside surface area if you take this, plus this, and revolve it around the axis. So let's do the outside surface area. The equation is surface area is 2 pi r bar times L. This r bar is going to be the sum of all the r tildes times their little length over the sum of all the length. I'm going to have a length segment right here. We'll make it a purple one. Then I'm going to have a length segment right here, make it a blue one. And then this is going to be a tiny area, but we may as well include it. A length segment right there, make it the red one. So when we're finding our centroid location, what I need to do is take each of those line lengths, they have a specific length to them, and multiply by their centroid distance measured away from the axis. So this line right here, every single point along it is 1.5 meters away from the axis. So its centroid is located 1.5 meters from the axis. So when we do the purple one, it's going to be 1.5 meters, and length is 4 meters, divided by the total length, which is going to be a 4. Now we need to add to it. What's the next one? Well, the next one is the hypotenuse of a triangle whose sides are 1.3 and 1.2. The length is going to be square root of 1.2 squared plus 1.3 squared. There's the length, whatever that number happens to be. Now, how far away is its centroid? Well, its centroid is going to be just right the absolute middle point of the line. How far from this axis is it? Well, we first have to go over 0.2 meters to get to the edge of the triangle, and then it's going to be half of 1.3. 0.2 plus half of 1.3, which is 0.85, which we don't need in the bottom of the fraction. The bottom of the fraction just gets the actual length. That is 0.2 plus 1.3 divided by 2. And then we do need one more term for that red strip. Its centroid location would be right at the middle, which will be 0.1 over plus 0.1, and then its length is 0.2. We add 2 down here, just the 0.2 for the length. Let's multiply the top and bottom of those fractions. So the top is 7.5238. That'll be meters squared. The bottom comes out to be 5.9692 meters. And if you divide those, you get 1.26 meters for the centroid location. Let's see if that makes sense given the picture. I think it does. Longest line segment is this 4-meter long one, and it's 1.5 meters away. But there's also a little bit of length that is closer in. So it's a little smaller than 1.5. That makes sense to me. Now let's go and calculate the surface area. Surface area is 2 pi times that r bar, which is 1.26 meters, and then the length is the 5.9692 meters. And as you might have noticed before, I could have just taken this number and put it in here because you're going to get 7.5238 again when you multiply that out. We get 47.27 square meters for the surface area of the outside of that. Now, I learned way back when I was in geometry probably that the surface area of a cylinder is 2 pi r times the height. So let's check that. If I took 2 pi times this radius times this height, I should get something that's a little smaller than this. So 2 times pi times 1.5 times 4. Yeah, I do. If we were doing just the cylinder part, 2 pi times 4 meters long times a radius of 1.5 meters, you get 37.7 square meters of surface area. This is a little bit bigger because we also have the slanted edge and that little piece on the bottom. So there we have another way to find surface area and volume using our knowledge of centroids.